What we're going to look at now is relating the thermochemistry to stoichiometry and how we're going to use that heat associated with a chemical reaction to actually predict how much product is produced or how much reactant is consumed. Okay, so let's look at an example of this. If I take 151 grams of ethanol and burn it in excess oxygen, I want to figure out how much heat is going to be produced from that. Okay, well, if I'm burning something, I'm doing a combustion reaction, so I need my overall balanced equation. I'm also going to need to calculate a delta H reaction if not given it. All right, but for this particular reaction, it's going to be a negative 1.235 times 10 to the third kilojoules. Also with these calculations, don't forget to note what's limiting and what's excess in these reactions. Remember, a limiting reagent is always going to limit how much product is produced, how much reactant is consumed, in this case how much heat is going to be given off or absorbed. Okay, so always take into account limiting or excess reagents. In this problem, we're told we have excess oxygen, so we don't need to worry about it. 151 grams of ethanol burns. Well, this is just like the other stoichiometry, except now instead of a mole-to-mole ratio from the balanced equation, we get a mole-to-heat ratio. But it still focuses around those moles in that balanced equation. So if I start with 151 grams of the ethanol, I need to get that to moles. Well, I do that using the molar mass. Once I have my moles of ethanol, then from the balanced equation I can say, well, 1 mole of ethanol is going to give me that negative 1.235 times 10 to the third kilojoules. I'm ending up with my units of heat, so I can stop there. So for 151 grams of ethanol, I'd get a value of negative 4.048 times 10 to the third kilojoules. Now keep in mind, when we're dealing with thermochemistry in these delta H reactions, those signs are just telling us, are we giving off heat or are we absorbing heat? So if I have a negative heat, is that an endothermic or exothermic process? Well, it's an exothermic process. What does that mean in terms of heat? Is it given off or is it absorbed? Well, if it's an exothermic process, it means heat is given off. Okay, so I'm not using up 4.048 times 10 to the third kilojoules. That's not what that negative sign means. It means it's an exothermic process. So in reality, I've produced 4.048 times 10 to the third kilojoules of heat. So pay attention to what the question is asking and note those signs, okay? Negative just means it's giving off heat. Positive means it's absorbing heat. All right, but as far as the calculation goes, we did the grams to moles and then just a mole to heat ratio. Okay, it's pretty straightforward. All right, let's look at another example of this. I want to know which one of these is going to produce more heat if burned, 34.5 grams of ethanol or 52.3 grams of butane. Well, let's start with the butane. Before I do any sort of calculation, I'm going to need to figure out delta H reaction for the butane. So to do that, I'd take that butane, I'd be reacting with O2, and I could calculate out a delta H reaction. Okay, so from that butane then, I take that 52.3 grams of butane, want to figure out how much heat is produced, well then I convert that grams of butane to moles of butane, and then moles of butane to kilojoules, right, based upon the chemical reaction of C4H10 burning. All right, and that's going to give me a negative 4.784 times 10 to the third kilojoules. Do the same thing with the ethanol. Convert my ethanol to moles, moles to heat, and I get a negative 9.248 times 10 to the 2 kilojoules. So which one of these is producing more heat? Once again, keep in mind that negative sign is just indicating that it's an exothermic process, it's giving off heat. So the butane is actually producing more heat, even though it's got technically the more negative value. Negative just indicates it's exothermic, it's giving off heat. So the amount of butane there gives off 4.784 times 10 to the third kilojoules of heat. The amount of ethanol gives 9.248 times 10 to the 2 kilojoules of heat. All right, another calculation. Let's say we take calcium carbide, react it with water to form acetylene and calcium hydroxide. We know the delta H for the reaction is a negative 127.2 kilojoules. And we know that we get 2.37 times 10 to the 2 joules of heat given off during one of the processes. So how many grams of calcium carbide were going to be consumed to produce that amount of heat? Well, I need to first get my balanced equation. Okay, I'm already given the delta H for the reaction. So now, I'm starting with heat. I know heat was given off, so that's exothermic, so my sign could be a negative. Now note, that's in joules, so I need to get it to kilojoules. Once it's in kilojoules, I know that I have a negative 127.2 kilojoules for every 1 mole of calcium carbide that reacts. And then I can convert my moles of calcium carbide to grams of calcium carbide. So if I get that much heat produced, I'd consume 0.119 grams of calcium carbide. All right, let's look at the same process, and let's figure out how many grams of water we're going to be consumed. Well, I need my balanced equation. Start with my joules again, take them to kilojoules, and now I do the negative 127.2 kilojoules to 2 moles of water. Why? Well, because there's a 2 in that balanced equation. Okay, so I have to pay attention to those coefficients. It's not always going to be whatever the delta H of reaction is to 1 mole of whatever I'm looking for. You've got to pay attention to those coefficients. All right, and then I know 1 mole of H2O is going to be 18.02 grams of H2O, and end up with that many grams of H2O. All right, so that's dealing with how many reactants were consumed. I can also use it to calculate how many grams of product were produced. All right, so balanced equation, start with my heat, convert it to kilojoules, use that heat to mole ratio from the balanced equation in the delta H of reaction, then do the moles to grams, and end up with that many grams of calcium hydroxide are produced in this process. Okay, so those are examples of different calculations dealing with thermochemistry and stoichiometry. Really what it comes down to is once you know the delta H of reaction for a balanced overall chemical equation, then it's just a matter of applying that to the mole to mole ratios, except now you're going to be dealing with a mole to heat ratio or a heat to mole, whichever way you need to go. That's going to be it for our thermochemistry and stoichiometry calculations.